Hello, algorithmicians. In this video, I'm going to go through the multiple choice answers for VCE Algorithmics 2025. I'll spend time explaining why the wrong answers are wrong, as well as why the right answers are right. If you're watching this and you're preparing for 2026 exams, make sure that you have downloaded the paper and tried the questions first, or failing that, at least pause the video as you go along, try the questions first. Like and subscribe if you want to see more, or just to show your appreciation. I'll be posting the answers to the written questions soon. With those and with this ones, note that I'm not affiliated with VCAR, these are just my suggested answers. So let's get into it. With these earlier questions, we know that most people get most of these questions right. So you want to do them as quickly as you can without making silly mistakes. So still read every question 2 or 3 times in your head. Question 1. We know that the quickest way of access, or the thing which allows the quickest access, is array. A graph, well, you've got to link to a graph from different nodes or have some kind of index. A set is kind of all right because it lets you quickly check the membership of the set of a particular item, but this question really has a sense of wanting to retrieve some information beyond just checking. So it's not set, and it's definitely not stack. Stack is last in, first out. We can only read the most recent item. So the answer is A. Question 2. What are the inputs and the outputs? If we want to add an operation to a queue, we need the queue and we need the item. So straight away, that puts us in the realm of B and C, and the output of that is the queue. So the answer is C. I can't imagine how anyone would think anything else unless you just didn't learn how signatures worked. Question 3. This is the first one which illustrates that algorithmics exams do require you to be a little bit versatile sometimes because, you know what, BFS and DFS are not design patterns, but we kind of know what it means. And if we've done any kind of revision, we would be thinking queues are related, oh goodness me, QUEs are related to BFS and stacks are related to DFS. So straight away, we're going to get rid of B. Divide and conquer could conceivably use breadth first search, although it's more likely to be recursive, so that's going to be a stack again. However, wouldn't say it's heavily relying, and dynamic programming, well, just no. So the answer is A. This one, when I'm doing this, I'm looking for ways to discount the nodes. So we can see that they're all the nodes themselves are laid out. We can see straight away A is wrong, which is a relief. A is wrong because we've got this J node here. Now let's see if we look at each of the graphs. We're trying to find an edge which is in the subgraph, which is not in the main graph, which lets us eliminate it. And straight away I can see CF there. So that means that B cannot be one. It doesn't matter that there's missing edges. We can see HI as well. So either of those mean that this is not one. So we know that's not one, that's not one. Can we find an edge here that yeah, okay, I can see the edge DE exists in C, but not in the main graph. So that's no good. That's the only one I can see, but I only need one. And then now we've got D, we'll just check. Yes, we've got DG. Well, I'm looking at these in the main graph. I've got DG, I've got AE, I've got EI, I've got AH, and I've got HI. So the answer was D. So question 5, we can see, is it one decision or many decisions? And is it fixed conditions or varying conditions? Well, we're not going to bother constructing a whole decision tree to make one decision. It seems rather unlikely, so straight away we can discard A and we can discard C. And when we've seen decision trees, hopefully we've noticed, I mean, the classic example is classifying a bird, and the way of classifying that doesn't generally change. So we have a fixed set of conditions and varying input data. I mean, varying conditions and fixed input data, well, that would be, well, it would seem unusual. So that one seems straightforward enough. Fix, we can see A is wrong. That seems like a description of breadth first search. Looks like B is correct. That's exactly what Prims seems to do. We can see that C is not how we work. And D is, I mean, maybe it's kind of, it's not really dividing a problem into multiple subproblems. It's more of a greedy algorithm. In fact, it's not dynamic programming at all. Sometimes we try too hard to make these things fit, and B is obviously the best answer there. 7, so we've got a bunch of locations around the place and we need to visit them all. That is a traveling salesman problem. So straight away we should be able to look at this and say it's D. Why the other one's wrong? Shortest path, it's not talking about just getting from one place to the other, so we can see A is wrong. The mineral spanning tree is to do with connectivity, so that might be connecting water supplies or something, so B is wrong. And single source, shortest path, again, that's getting from one place to another. So I don't think I explained that very well. For A, we're looking for the shortest distance between all pairs of places, which we might have used in order to find the traveling salesman problem, but that wouldn't be the best solution. So answer is D. This is almost exactly the 0-1 knapsack problem, except your knapsack is large and truck-shaped. So why is it doing that? There we go. Minimal spanning tree. I mean, there's just nothing about these that would conceivably be right. That's not a very good explanation, but I don't think anyone's going to be sitting there thinking, why is it not the graph coloring problem? Right. Now, this one, we do have to work through these and do like a little trace. So let's call iterative factorial on n equals 5, just to start with. And then we would say, so we've got result is being stored as 1. And then for I in 1 to n, we can do result equals 1 times I. So I 1 times 1 is 1. Then we have I equals 2. Result equals 1 times 2, which is 2. I equals 3. Result equals 2 times 3, which is 6. And so on. Then I equals 4. 6 times 4 is 24. And 5 times 24 is 120. So, and we know that that's what 5 factorial is. 5 times 4 times 3 times 2 times 1. So it looks like A is correct. Let's look at the other ones. And if we know how factorials work, we can pretty quickly get rid of the things where we're adding, because, I mean, why would this work? Perhaps I'll work through this anyway. If you don't want to see, you can just skip. So we've got the result is stored at 0, and then I is stored at 5, and the result is result plus 5, which is 5. The result is the result plus 5, which is 5, and then this goes down to 4. Then we have 9. I mean, yeah, we can see this isn't going to increase like factorial increase. Okay, definitely not B. But C. Now, I mean, if we looked at these, we can probably tell it's going to be A and C. I mean, D has got a bunch of division in there, so I probably wouldn't have bothered to try B, and I'm not going to try D either. Let's, again, if we've got the time to try and get this right, this might be one of those questions that you come back to. So, let's say n equals 5. The result is set to 1, and while n is greater than, we've got to be careful on the conditions here. So while n is greater than 1, we do result equals 1 times n minus 1, which is 4, and then we decrement n, so n is 4. Is n greater than 1? Yes, it is. So we do 4 times 3, which is 12. We reduce it by 1, reduce n by 1. We do 12 times 2, which is 24. Yeah, we can see this isn't going to get to 120 as well. So the answer was A. And 10. Hopefully, if you know what all these things mean, then it's kind of obvious that the answer is D. Knowing whether or not your computer, your algorithm is mimicking artificial intelligence is really not relevant. Whereas a support vector machine could be used to separate people into healthy or unhealthy, at risk or not at risk, that sort of thing. So A is okay. The neural network might give us a more nuanced response as to somebody's diagnosis, and a decision tree is a kind of white box environment, so we can see why somebody, whether somebody is healthy and why. So the answer there is D. Question 11, we just need to know how merge sort works. We would have split the array down into two equal parts and then into those arrays into two equal parts and so on. And then we would end up sorting these. So this one would come back up as 1, 5, and 12. This one comes back up as 4, 8, and 10. And when it comes back up to here, we're going to have 1, 4, 5, as in we're going to have this whole thing sorted out. So 8, 10, 12, which is B. So we can see that the C and D are sort of, they're going to be sort of related to deeper parts of the problem, but that's not the first left call because it says the left call of the algorithms that are just the very top. So it's not that one, not that one. And that's just, that will be the final answer. So the final step of the algorithm will merge our array 1, 4, 5, 8, 10, 12 with the one on the right, which I haven't written, and that will give us 1, 2, 3, 4, 5, 6, and a whole bunch, and the rest of the numbers. Question 12. So if we're thinking backtracking, we are thinking recursion. If we're thinking recursion, we are thinking stack. An array is not going to help you queue. Well, we always undo the last thing first, so that wouldn't be the queue, and the linked list, again, like an array, is just irrelevant. So yeah, what to remember there, backtracking is recursion, recursion is stacks. Question 13, reckon this one is going to be A star. So we have to choose, if we're trying to get from one place to another place efficiently, we've got to choose, it's a single source shortest path, so it's definitely neither of these guys. Then we want to get there quickly, so we'd use some kind of heuristic. The fact there are obstacles doesn't mean we can't use A star. I mean, it's really just, we can imagine, let's say we've got a space, we could then model that space as a graph, essentially with a series of nodes. You know, we can go from here to here to here to here, and there would be different distances to get to each of the available spots. And there's no reason we wouldn't use A star, because in general we want to be going towards from the bottom left to the top right. And suppose the room was bigger, we want to make sure that we are going in this direction and not exploring all of the paths around here to try to get to that top right thing. So A star is going to be better than Dijkstra. This one is kind of hard. I think we can rule out some of them if we know our basics fairly quickly. We should be able to rule out A because we've established the N-Sharding's problem is negative. And if you put B, well, I'm not sure where you were. So we're looking now at C and D, and this is tough because, I mean, Alonzo Church doesn't tend to feature in many people's explanations of this. Now, if you know the history, you'd know that Turing came after Church, so that's one reason that C is wrong. But there's every chance that you wouldn't know that, so let's consider D. We hopefully at least know that there is a reducibility between Turing's work and Church's work. We know that Turing machines are equivalent to lambda calculus. And so if you were just guessing, the idea of solving two lambda calculus expressions being equivalent, and what we're saying is we want a function which determines whether any two lambda functions are equivalent. And we can sort of think, well, that's going to be to do with the halting problem. So that is going to be D. So what we're talking about there is what to do. Perhaps if you're not entirely sure, which is the one of these answers that makes the most sense, in case you haven't happened to read this particular bit of history. Question 15, I heard some people talk about this saying it's a bit unfair. I mean, I reckon there's a fairly clear answer here. How does this differ from the travelling salesman problem? Well, I think it's obvious that not every destination has to be visited. I don't think it's likely we would visit destinations more than once. And he's doing a day trip that starts at his hotel. Well, that suggests to me that he's going to be returning to his hotel. So, yeah, starting location does need to be returned to. D is definitely wrong. The distance between destinations does not change. So I think A is the best answer there. 16, they're all fairly similar, so I would scan through these first. And having just read D, artificial intelligence candidate question, blah, 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 Whether the computer or the human is more intelligent? No. The idea is we're trying to see, can we distinguish the human from the computer? So that sounds, well, no, I was looking at C there. Two humans are questioned by an artificial. No, we know we have a panel of judges who are questioning a human and a computer. So, looks like B, doesn't it? Artificial intelligence candidate and a human player are questioned by an interrogator who must determine which is human, which is not. And if he cannot, then the Turing test is passed. Let's just read why is A wrong. So we're not distinguishing between whether ChatGPT is better than Grok. We're deciding, can Grok imitate a human? So the answer is B. Question 17, I love these. We should just be turning the handles. So we can see that A is 1 because there's just one function call. B equals 2 because they're half the size. C is 2 because the highest power in the function outside the recursive call is squared. Then we look at the cases. We've got b to the power of c, so 2 to the power of 2 we can see is greater than 1. So we are dealing with this case here, which gives us big O of n squared. So the answer is B. Let's see, we're now getting into the slightly hairier questions. We know in general, when we have some data, we need to separate our data into training data and validation data. We train our model on the training data, and then we check to see how well it works, how well it recognizes on the validation data. So looking through these, we can see A is wrong because we haven't split the data up, because we need to make sure the key thing here is that we must keep our training and our validation data separate. So we can see that A is going to be wrong. B, well, is not at all. We've got no training data at all there. So between C and D, they sound quite similar. In fact, they read exactly the same until this last line here, resample the train and test sets. So this is the bit that makes D incorrect. It sounds a bit like what is correct, which is where we can take the validation data and we can have different validation sets. So we can have validation sets and then maybe change the parameters if we need to. But this makes D incorrect because what we're saying is like remixing all of the training and the validation data each time. And if you do that, you're going to end up essentially all the data becomes scene data. We don't have true validation data. So the answer was C. Question 19. This is actually a relatively gentle one. I don't even know what A is supposed to mean. We know definitely B is wrong because big O is the upper bound. So now we're really looking at C and D. C is, I reckon it's fairly clearly wrong because we know the whole point is we're abstracting away from the actual time. We're not saying this algorithm takes 10 seconds, this algorithm takes 15. What it does allow us to do is ignore all those details, the constants, the multipliers, and concentrate on the time and space trends of algorithm. So just very hand-waving-y. What happens when the numbers here get very, very big? How does one algorithm perform, perhaps compared to another one? And finally, I think some of these are quite easy to cross off. We know randomized search will not have an optimal, doesn't guarantee, and I think we can say that randomized search does sound more efficient. I think where people will have struggled with this is knowing that randomized search is a category of searches which includes simulated annealing. So we could have randomized search, which is just truly random, and we know that there is an element of randomness to simulated annealing. So we need to distinguish between B and D. And what I've shown you here is a search space which is differentiable, which makes hill climbing very good. So what I've got on the bottom right, this is a nice search space to use for hill climbing, whereas we want to use simulated annealing, let's say, when we can't differentiate the function. So that's when we're expecting there to be maybe a jagged search space and we want to have a random jump from here to here. So randomized search will help us where we don't have that differentiable heuristic function, whereas randomized search actually has potentially more hyperparameters to tune, especially if we think about it as simulated annealing. So that makes B less good. But ultimately, that is the nature of algorithmics. They're going to be, like for example, words like hyperparameters. I haven't seen that come up before. The hyperparameter is the one that you set on the model. So it might be with simulated annealing, it might be the rate of cooling, for example. And then the parameters themselves are the things inside the model which we are optimizing through the training process, which is like the inside of the neural network or whatever. So I hope that helps. Say click like and subscribe. In a few days, I will be putting out a longer video going through all of the extended response, looking at some good answers, some bad answers. Feel free to leave any comments.